Hello students, in this video lecture we are going to discuss about the last topic in Unit 2 Communication and Computer Gadgets, that is microwave oven. Every era has contributed its own idea and convenience to the kitchen. For the open stove to the closed one, from wooden to oil, coal, electricity and gas. And now the age of microwave is here. Furthermore, microwave ovens were considered as a luxury. For a long time, people considered that microwave ovens are used for reheating foods only. But as the pace of modern life has got faster and busier by the day, microwave cooking has provided extremely helpful in the efficient pre-preparation of daily food in the shortest possible time. A microwave is a signal that has a wavelength of 1 foot, that is 30.5 centimeters or less. This converts to a frequency of 984 MHz. So all frequencies above 1000 MHz, that is 1 GHz, are considered microwaves. The frequencies immediately below this border are considered ultra-high frequencies. The upper end of microwave range contains the light frequency about 10 to the power 15 Hz. However, because electronic transmission is so closely geared to half wavelength devices, the practical upper limit is about 300 GHz, where one wavelength is about 0.04 inches, is 0.1 centimeters. Smaller devices are being made, but their power handling ability are also micro. Normally, microwaves spread outward as they travel through the atmosphere and disappear without effect. The microwave oven uses microwaves of frequency 2.4 GHz to cook food. Microwave ovens have a magnetron usually concealed in the roof of the oven, specifically designed to make use of energy in the microwaves. Electricity applied to the magnetron tube is called to create the microwave energy. Microwaves enter the cooking area through opening inside the oven. A turntable or tray is located at the bottom of the oven. Microwaves cannot pass through the metal walls of the oven, but they can penetrate such materials as glass, porcelain, and paper. The materials out of which microwave-safe cookware is constructed. Microwaves do not heat cookwares, though cooking vessels will eventually get hot from the heat generated by the food. Microwaves reflect off the metal components in the oven. These metal parts prevent the escape of microwave energy. All microwave activities remains inside the oven. When the door is opened or the oven is switched off, the production of microwave stops initially, and induction in series with the terminals. Both effect limits the usefulness of the device at a high frequency value of 2 picofarad and 0.02 microhenries, or typically inter-electrode reactance that erodes the high frequency signal. A second limitation is the time it takes for the electrons to travel from one electrode to another electrode, called the transit time. A microwave frequency, the time for one cycle of RF energy is often shorter than the transit time of the device. The measures required to improve one effect are the opposite of what is required to improve the other, and are therefore counterproductive. For this reason, the principle of using the transit time instead of fighting it has become basic to many of today's microwave devices. Let us first discuss about the Megatron. The word Megatron is a conjunction of the word magnet and electrons and identifies one of the major components, a very powerful magnet. The second major component is a cylindrical copper block drilled and channeled as shown in the figure. The center opening is called the interconnection chamber. The holes drilled around the outer edge has a diameter equal to 1/2 wavelength at the operating frequency and are called resonant chambers. There will always be an even number of resonant chambers, usually not less than 6, and not more than 16. With a magnetron used as a diode, the copper block becomes the anode and a directly heated cathode is placed at the center of interaction space. The chamber is sealed with top and bottom cover plates and the air is drawn out to form a vacuum. The output connection is a wire loop in one of the chamber that feeds to a coaxial cable fitting on the side wall of the block anode. Because the anode is exposed to the user, it is placed at the ground potential and the cathode is at a high negative potential. The magnetron will only operate as an oscillator and finds its greatest use as a power oscillator. The frequency of magnetron will remain most stable when any one channel differs in phase from its immediate neighboring channel by an exact multiple of pi by 4 radians. Best results are obtained at 4 pi by 4 radians, that is 5 radians, that is equal to 180 degree. This is called the pi mode of operation. To ensure this phase shift of 180 degree, alternate channels are strapped together. Next, we will discuss about the waveguides, the part of a microwave system that establishes the theory of operation for all of the other devices is the interconnecting hardware called waveguide. The conductors of microwave energy constitute a departure from conventional cable in that they resembles a coaxial cable with the center conductor removed as shown in the diagram. The microwave energy is carried through the waveguide by reflecting along its inside wall. This is possible only if the guide is larger than one half the wavelength of the applied voltage wave. Thus, the waveguide size is directly related to frequency. The waveguide factors the desired attentions are attenuation loss, size selection, coupling method, guide impedance, and power handling ability. By transforming microwaves into 3D waves, the system ensures that every inch of food being cooked is immersed in 3D microwaves, resulting in food that is cooked more evenly. Microwaves transformed into three-dimensional waves come out of special designed waveguide. Microwave oven block diagram. The block diagram of a microwave oven is shown here. The main plug and socket are 3 pins earthing type. The fast blow ceramic fuse is of 15 amps 250 volts. Interlock switches are linked with the oven door. Power will be applied to the main transformer only when the oven door is closed. At least one interlock switch is in series with the transformer primary, hence even a spot of dirt in the relay or trial cannot turn the oven on when the door is open. There is yet another interlock across the power supply line. It is normally remains open. If the door alignment is not correct, it will be activated, putting a short circuit across the line and making the fuse to melt. Thus, the microwave oven is a fail-safe device. The voltage induced in the secondary winding is about 2000 volts at 250 milliamps for normal domestic ovens. The transformer also has a tertiary winding for the magnetron filament. The high voltage return circuit is fastened directly to the chassis through the transformer. A half-wave doubler configuration is used for the rectifier with a peak inverse voltage of about 12,000 volts. One end of the diode is connected to the chassis. The blender capacitor should always be discharged before touching anything inside when the cover is removed. The high value blender resistor is slow to discharge, further it may be opened. The thermal protector is a PTC thermistor. The primary current decreases when the temperature rises abnormally. It senses the temperature of magnetron as it is bolted to the magnetron case and is so connected electrically that its resistance comes in series with the primary circuit. The controller is a microprocessor chip with the clock. It is activated by keypad switches and sets the clocking time. It senses the temperature and moisture, sets the power level and runs the display. There are three power levels. For high, the microwave generator remains on continuously. For medium, it remains on for 10 seconds and off for 10 seconds. For low, it remains on for 5 seconds and off for 15 seconds. The controller activates the microwave generator using either a relay or a triac. LCD timer with alarm. Most microwave oven features at least one timer with an alarm. Older applications used mechanical timers, but modern microwave ovens and cooking ranges features electronic timers using digital circuitry. The concept of a timer is shown here. In this, the keypad is the input and both the digital display and alarm buzzers are the output devices. The processing and storage of data occurs within the digital circuit block. A somewhat more detailed block diagram of digital timer is also shown as figure B. The digital circuitry block has been subdivided into four blocks. They are the time-based clock, the self-stopping down counter, the latch decoder driver, and the magnitude comparator. The input control blocks presets the time held in the down counter. The time base is a stable multivibrator which generates a known frequency. In this case, the signal is 1 Hz square wave. The accuracy of the entire timer depends on the accuracy of the time-based clock. Activating the start input control causes the down counter to decrement. Each lower number is latched and decoded by the latch, and this block is also driven by the display. Single chip controllers. Most of us are familiar with the general purpose microcomputers such as IBM and Apple Macintosh, which are used in more than half of our homes and almost all of our businesses. These microcomputers can perform a wide variety of tasks in a wide range of applications depending on the software they are running. There is a more specialized type of microcomputer called a microcontroller, which is not a general purpose computer. Rather, it is designed to be used as a dedicated or embedded controller which helps monitor and controls the operation of a machine, a piece of equipment, or a process. Microcontrollers are microcomputers because they use a microprocessor chip as the CPU, but they are much smaller than general purpose microcomputers because the input output device they normally uses are much smaller. In fact, some of the input output devices as well as memory are usually right on the same chip as the microprocessor. These single chip microcontrollers are employed in a wide variety of control applications such as appliance control, metalworking machine, VCRs, automated teller machine, photocopiers, automobile ignition system, anti-clock brakes, medical instruments, and much more. A very simple application of an embedded microprocessor is a microwave oven control system. A block diagram of such a system is shown in the figure. If we So that's all with Unit 2. The first topic what we are going to discuss in Unit 3 is washing machines. From the first washing tool, a broom with 4 fingers at the bottom to move the clothes around the bucket, to the modern fully automated ones, washing machines have come a long way. Technological advancement have brought about metamorphic changes in washing machines. From manual washing machine requires hot water, so before dirty clothes got crunched in machines to semi-automated with spin dry facility to fully automatic and now recently introduced fuzzy logic and concept of machine was has totally changed. Multinational companies dealing in electronics have launched new and modern techniques in washing machines. In today's high stress life, a washing machine has become a household necessity. Washing machines are gradually emerging as an omnipresent Dobby in Indian homes. Fortunately, the choices are many, not only in colors, design, and features, but also in price. Of course, the market is flooded with washing machines offering a range of operations from semi-automated to fully automated, from top load to dumbbell wash. These state-of-art machines promises multifarious, user-friendly features at down-to-earth prices. The task here is to simply to identify the input and output device used in electronic washing machine and to construct a block diagram showing their connections to controller. Detailed information about the characteristics of sensor and activators can be added at a later stage. The block diagram shown in the figure shows a possible representation of the system. There are many acceptable ways of presenting the system. It would, for example, be possible to consider the display to be internal to the controller and therefore not shown it separately. Similarly, clock circuitry used to time the operation of the machine is considered here to be contained within the controller. It could equally well be constructed as an external component. The block diagram is a good start point for the generation of the specification since it shows very clearly the structure of the complete system. The block diagram makes no assumptions of the form of the controller. It would be implemented using a electromagnetic timer or a microcomputer or a range of other technologies. Many modern washing machines now uses microcomputers to control their various functions, replacing the electromechanical controllers used in earlier. Clearly, it is not practical to consider all aspects of such a system, but it is instructive to look at some elements of the design. At various stages of washing machine, the drum is required to rotate at different speeds. These includes a low speed of about 30 revolutions per minute while cloths are washed, an intermediate speed of about 90 rpm while the water is pumped out, and a high speed of either 500 or 1000 rpm to spin dry the cloths. Let us consider how the microcomputer should control the speed of the motor. Since a domestic washing machine is a very high volume product, the design should attempt to minimize the amount of hardware required. These necessities a close look at the choice of sensor and activators to select low cost items. Our first decision must be whether the system will be open loop or closed loop. Since although an open loop system is theoretically possible using a synchronous motor, the cost of such a system for high power variable speed application is prohibitive. The system will therefore be closed loop using a motor to drive the drum and some form of sensor to measure its speed. One of the simplest method of speed measurement is to use a counting technique illustrated in the figure. It uses a fixed inductive sensor to produce a pulse each time it is passed by a magnet which rotates with the drum. This produces one pulse per revolution of the drum which can be used to determine its speed. The speed of the motor will be controlled by the power dissipation in it. The simplest way of speed control is to use a triac. The power collector could be controlled by some form of electronic circuitry, but the hardware requirement can be reduced if the microcomputer controls the power directly by firing the triac at an operating time during its cycle. To do this, the controller must detect the zero crossing of the AC supply. This will require circuitry to detect the crossing point while protecting the processor from a high voltage. A block diagram of the system is shown in the figure. At any time in the washing cycle, the program determines at what speed the drum should rotate. For a knowledge of the required speed and the actual speed as obtained, the controller can determine whether to increase or decrease the power dissipation in the motor. The motor power is determined by the timing of the track firing pulse. If the track is fired at the beginning of each cycle of main cycle, it will remain on for the remainder of half cycle and the motor will operate at the full power. The longer the processor waits before firing the track, the less will be the motor power. The processor thus varies the delay time with respect to the zero crossing point of the main by appropriate amount to increase or decrease the power in the motor as determined by the difference between the actual and required speed. This method of controlling the motor speed is very processor intensive. It consumes a large amount of processor time and it will require a considerable amount of effort in writing and developing the software. However, this approach uses a very little hardware and is thus very attractive for such a high volume applications. Washing machine hardware. A system is an assembly of components united by some form of regulated interaction to form an organization for. We will examine a microcomputer system using a washing machine control as an example. The input peripheral consists of temperature sensor, that is, this is nothing but of the temperature sensor, and it consists of a safety cutoff switch, keyboard for program selection, water level gauge, motor for washing drum, power switch for motor and heater, heater for washing water, water inlet valve, water suction pump, and finally the control lamp and indicator. The unit listed here are in the washing machine as well as its mechanical components, the electrical units and the electronic components. These are all nothing but of the hardware of a washing machine. Fuzzy logic washing machines are gaining popularity. These machines offer the advantage of performance, productivity, simplicity and less cost. Sensor continuously monitors varying conditions inside the machine and accordingly adjusts operation for the best wash results. As there is no standard for fuzzy logic, different machine performs in different manner. Typical fuzzy logic controllers has the washing process in such a way that it will intake the water temperature, wash time, rinse time and spin speed. This optimizes the lifespan of washing machine. More sophisticated washing machines weigh the load, advise on the required amount of detergent, assess cloth material type and water hardness and check whether the detergent is in the powder or liquid form. Some machines even learn from past experience, memorizing programs and adjust them to minimize running cost. Diagnostic fault finding system displays a fault code if any problem arises. You can then convey this fault code to the service center, thus ensuring the required repair technique reaches the right part to fix with. Machines with fuzzy logic microprocessor can be updated as and when a new technology or program comes up. Several models of internet-enabled washing machines have been launched. When the network home becomes a reality, these machines will allow downloading of new programs and remote fault diagnosis over the direct internet connection. Most fuzzy logic machine features one-touch control equipped with energy-saving features. These machines consume less power and are worth paying extra for if you wash full load more than 3 times. So that's all with today's video lecture. See you all in the next video lecture. Thank you.